Hello and welcome back. We are on chapter 14 of Materials Kinetics, which is on the topic of nucleation and crystallization. Today, we are going to cover both the thermodynamics and the kinetics of crystallization. This is in the context of classical nucleation theory, including both homogeneous and heterogeneous nucleation. We will then develop the physics of crystal growth rate, and putting the nucleation and crystal growth rates together, we will be able to calculate time temperature transformation diagrams. And an example of controlling nucleation and crystal growth rates is glass ceramics, which will be covered at the very end of the lecture. So with the kinetic theory of crystallization, the main assumption here is that crystallization involves two steps. First, there is a nucleation step, and then following the nucleation step, there is a crystal growth step. So if we want to avoid crystallization, the system needs to avoid either one of these steps or reverse the order of the steps. On the other hand, if we are trying to develop crystals and grow crystals in a controlled fashion, then we want to control the nucleation rates and the crystal growth rates. But the key is that it's a two-step process and it has to occur in order. First nucleation followed by crystal growth. So the following steps are needed to determine the overall degree of crystallization. First, we must calculate the rate of nucleation as a function of temperature. Then we must calculate the rate of crystal growth, also as a function of temperature. And then we have to combine these two rates to determine the overall volume fraction of crystallization. And the combination of the nucleation and crystal growth rates leads to an equation that is called the Johnson-Mehl-Avrami equation. So let's start at the beginning with nucleation. First, a nucleus in this context is defined as being a precursor to a crystal. It is a periodic assemblage of atoms without a recognizable growth habit plane, or in other words, it's a collection of atoms that is kind of providing the seed for what will become a crystal. So it has some local order there with the structure. A crystal is an assemblage of atoms in a regular periodic array with recognizable growth habit planes. So the crystal is going to grow from the nucleus, but in order for that to happen, this precursor to the crystal, this nucleus, must form first. And nucleation occurs because the atoms, let's say the atoms within a liquid, are constantly vibrating and moving around as a result of the thermal energy of the system. Now, if that vibrational frequency is given by nu and the number of atoms per unit volume is given by n, the nucleation rate would be simply n times nu if every single vibration would allow an atom to become part of a nucleus. So in other words, if every single vibration is a successful attempt to form a nucleus, then the nucleation rate is simply that number of atoms per unit volume times the vibrational frequency. And that would give you the number of new nuclei that form per unit volume per unit time. However, this is simply an ideal upper limit because in reality, there are two barriers that have to be overcome in order for successful nucleation to occur. And those are called the kinetic barrier and the thermodynamic barrier. The kinetic barrier, which is here denoted as delta E sub D, is the activation energy that's required for an atom to cross the interface between the liquid and the nucleus. This may involve breaking of bonds with its nearest neighbors and certainly some realignment of the structure into a more ordered structure with that of the nucleus. The thermodynamic barrier is W star, and this is the net free energy change that results from the formation of a nucleus, specifically a critically sized nucleus, as we shall see. And if we account for both the thermodynamic barrier here, W star, and the kinetic barrier, delta E sub D, what this means is that every vibration is an attempt to form a nucleus, but in order to be successful, it has to be successful in overcoming both the thermodynamic barrier and the kinetic barrier. So we need to multiply this n times nu with two Boltzmann probability factors that give us the probability of success of overcoming the thermodynamic barrier, which is e to the minus w star over kt, where k is Boltzmann's constant and T is absolute temperature. And then another Boltzmann probability factor, e to the minus kinetic barrier over kt. And if you multiply these both together, that would give you the probability of overcoming both barriers. And so the actual nucleation rate is a lot lower than the ideal nucleation rate because it's only successful if it is able to overcome both the thermodynamic and the kinetic barriers. Now, one way that we need to classify nucleation is by either homogeneous or heterogeneous nucleation. Homogeneous nucleation is defined as the chance assembly of a number of atoms to form a group that leads to the lowering of the net free energy of the system. The probability of such an assembly is equal everywhere throughout the material. Or in other words, homogeneous nucleation occurs throughout the volume of a liquid, and homogeneous nucleation occurs at the same rate no matter where you are in that liquid, assuming that it is homogeneous and free from any surfaces or interfaces. If you have a surface or an interface, then the type of nucleation that we deal with is called heterogeneous nucleation. So with heterogeneous nucleation, the presence of a surface or an interface can act to lower the thermodynamic barrier for a nucleation and therefore can act to accelerate the rate of nucleation. So if you have any types of surfaces or interfaces, this might be surfaces with the wall of the container, or maybe the surface that's exposed to air, or maybe you've seeded the liquid with some initial crystals to start. Any of these things can provide surfaces that lower the thermodynamic barrier for nucleation. And in that case, nucleation that occurs at those interfaces or surfaces is called heterogeneous nucleation. So let's start with homogeneous nucleation, the simpler case, and then we'll build heterogeneous nucleation on top of that. Now, what we're going to do is describe nucleation in the context of classical nucleation theory. And classical nucleation theory makes a few assumptions. First is that it assumes that the nucleus is spherical, because it's easier to deal with the physics of a nucleus if it is described as a sphere. And it's also assumed to have a sharp interface between the nucleus and then the disordered matrix phase, for example, the liquid phase. And therefore, the change of free energy for forming a nucleus has two terms to it. There is a volumetric term here, which is just the volume of this assumed spherical nucleus. So that's 4/3 pi r cubed, where r is the radius of the nucleus, times delta G sub x, where this delta G sub x is the volumetric change of Gibbs free energy as a result of forming that nucleus. So if we plot this term here, this gives us the green curve shown on the right, where this is the change of free energy as a function of increasing the radius of the nucleus. And if we are at any temperature below the liquidus temperature, then this delta G sub x would be negative, meaning that it is thermodynamically favorable for the system to crystallize. And so as a function of the growing R, this green curve is going down in free energy, follow to the third power of R. So this is acting in a thermodynamically favorable direction. Now, at the same time, if we are forming a spherical nucleus with a sharp interface between the nucleus and the liquid, there is a free energy penalty that we have to pay by forming this interface where one didn't previously exist. And that's because you don't have perfectly good alignment between the atoms within the nucleus and the liquid, because the structure is different between the nucleus and the liquid. And therefore, we have a surface tension that's associated with that interface. That surface tension is given by gamma. That is simply the free energy penalty of that interface per unit area. And we multiply by the area of the interface. So this is just the surface area of the sphere, which is 4 pi r squared. And this gives us a positive contribution to the Gibbs free energy. And so as a result, the blue curve here shows the surface energy term, 4 pi r squared gamma. This is thermodynamically unfavorable because it's leading to an increase of the free energy of the system. So we have two different effects here, one of which favors the formation of a nucleus, that is this volumetric effect, this negative green curve that decreases with this cubic dependence of R. And then the other is this thermodynamically unfavorable term related to creating the interface. This is the positive contribution to the Gibbs free energy, and this increases as R squared. And because we've got an R squared term and an R cubed term operating in opposite directions, when we add them together, we get this shape of the black curve, where at small values of R, so for very small nuclei, the surface energy term is dominant. And so this black curve is dominated by the surface energy curve for these small values of R. And it's not until we get to large values of R that the volumetric term becomes dominant. So for small nuclei, the surface energy penalty is the dominating factor. And at large values of R, larger sizes of the nucleus, the volumetric decrease in free energy is the dominant factor. And you can see that there's a trade-off between these two terms where the overall free energy, as you increase the nucleus, initially it increases, goes through maximum, and then decreases. And what this means is that there is a region here where a nucleus is thermodynamically favored to shrink and disappear, and a region where it's favored to grow. So if you are at any sized nucleus between 0 and the location of this maximum here, which is defined as R star, so any nucleus that is smaller than R star, the negative direction of the free energy, or in other words, the downhill direction of the free energy, is moving towards a smaller and smaller value of R. In other words, for any nucleus that is of a size R that's less than R star, that can lower the free energy of the system by shrinking, by going to smaller values of R until it disappears and reaches 0. So any nucleus that is of a size smaller than R star is unstable, and it's thermodynamically favored to shrink and disappear. On the other hand, if you have an R that is greater than R star, now on this side of the curve, the downward direction is to grow the nucleus, because if we want to lower the free energy for anything that's R greater than R star, the downhill direction of the free energy is to increase R. So any nucleus that is of a size that is greater than R star is stable, and it is going to grow. So the critical value here is really R star. A nucleus that is at least as big as R star will be favored to survive and grow. A nucleus that is less than R star will shrink and disappear. And we use this value of R star to get the thermodynamic barrier for nucleation, which is the work associated with forming a nucleus of that critical size R star. In other words, if we evaluate the change of Gibbs free energy that is required to form a nucleus of that size R star, that gives us W star, the critical work that has to be overcome to form a nucleus of that size. And that is the thermodynamic barrier for nucleation. Now, the way that we get this is straightforward. We have our equation here for the change of Gibbs free energy that accounts for both the volumetric term and the surface energy term. So this equation here is for this black curve that is plotted. In order to find the location of this maximum, we need to take the derivative of that with respect to R, and that is what's being done here. So this is the derivative of the change of Gibbs free energy with respect to the radius R, and taking the derivative of the volumetric term, that gives us 4 pi R squared times delta G sub x, and the derivative of the second term is 8 pi R gamma. Now, to find the location of this maximum, we need to set that derivative equal to 0 and solve for R. we immediately divide by one of the r's because one of the solutions is r equals 0. That's not the solution that we're after here. The other solution, when we solve for r, gives us r star equals -2 gamma over delta G sub x. So this value here, r star, is this location of this maximum in the Gibbs free energy. That is the size of the critical nucleus for it to be stable. The reason that there's a minus sign here is that this gamma is a positive number and the delta G sub x is a negative number, as you can see in the green curve. And so the minus sign out in front with a negative denominator means that the r star is a positive number. So this gives us the equation then for the size of this critical nucleus, which depends on just this ratio between the surface tension gamma and the volumetric Gibbs free energy change delta G sub x. In order to get W star, this work associated with forming a radius of critical size, we just take this value of r star here and we plug it back into our initial equation for delta G and then solve for what the delta G is, and that gives us W star. So we take this value of delta of r squared, stick it in for this r cubed term, stick it in for this r squared term, and simplify from there. So that's exactly what we're doing here. We're taking our equation for the total Gibbs free energy and what we just solved for r star. We stick this into the cubic term here for r cubed and for the squared term. And when we perform those operations, so perform the cube and perform the square, you get these two fractions here, and then getting a common denominator by multiplying this second curve here, or the second term by 3 over 3, combining the like terms. Overall, then, the W star, this work for forming a critical size nucleus, or this thermodynamic barrier for nucleation, is 16 pi gamma cubed over 3 delta G sub x squared. So it is a function of the surface tension cubed and the volumetric free energy change squared. Of course, this is all assuming a spherical nucleus. So that gives us the thermodynamic barrier in the case of homogeneous nucleation. If instead we have heterogeneous nucleation, then we have introduced some sort of surface or interface to the system that could potentially lower that thermodynamic barrier for nucleation. So for example, if you've got a liquid state here, L, and you've got a nucleating crystal cluster here, X, and then you have some sort of solid substrate or surface here, S, then there are 3 different surface tensions that are relevant here. It's not just the one surface tension that we had in the case of homogeneous nucleation. Here now we have 3 surface tensions. So there is the surface tension between the liquid and the nucleating crystal. This is the same surface tension that we had previously, and here it's labeled as gamma with the subscripts Lx for liquid crystal. We also have the surface tension between the nucleating crystal and the solid substrate, that is gamma xs. And the third surface tension is the surface tension between the liquid and the solid substrate, that is gamma ls. So we've got these 3 different surface tensions, and the balance among them is going to give us this contact angle here, theta, according to Young's equation. So if you consider this interface having interfacial forces acting in the leftward direction, and these two, this one is acting entirely in the rightward direction, and then the gamma Lx has a component that's acting in the rightward direction, which is gamma Lx times the cosine of this contact angle theta, that these two have to balance. All the leftward acting forces balance with the rightward acting forces. And if you write the equation for that balance here, you get the Young's equation. So gamma Ls acting in the leftward direction. In the rightward direction, you've got gamma Xs plus gamma Lx times the cosine of the cosine of theta. And therefore, this gives you the equation for the contact angle. And the contact angle is really the key parameter that governs how much the thermodynamic barrier is reduced by with heterogeneous nucleation compared to homogeneous nucleation. So if we still assume that the overall nucleus would be spherical, but it's a sphere that is cut off by the substrate. So this is just like the top part of a sphere here. With that geometry, if we solve for our star, the critical size nucleus, we get the same value as before. It's still just -2 gamma Lx over delta G sub x, where this is still just the gamma between the liquid and the crystal. So there's no change of the size of the critical nucleus between homogeneous and heterogeneous nucleation. It's exactly the same R star. The difference is in the work of nucleation in the heterogeneous case, and that is equal to this term here, which is what we just derived for the work of the homogeneous case, times this geometric factor, which depends on the contact angle theta. And so this, we can write this as just that the work of heterogeneous, the thermodynamic barrier for heterogeneous nucleation is equal to the thermodynamic barrier for homogeneous nucleation times this geometric factor that depends on the contact angle. And we can consider a couple of limiting cases here. If you have a perfectly wetting substrate, so if the nucleus perfectly wets the substrate, then the contact angle here, theta, would go to 0. And if you put in a contact angle of 0 here, then this entire term goes to 0, which means that the thermodynamic barrier for heterogeneous nucleation is 0. Now, where this would happen is if you are trying to grow a crystal of a particular type, and if you seed the system with exactly the same crystal of the same type, then you've eliminated the need to even form a nucleus because you've already seeded it with the crystal that you want to grow, which means that you've already gotten perfect alignment between the atoms that would form of that nucleus and the atoms in the crystal, since they have exactly the same structure. So in that case, that's an example of what's called epitaxial growth, which would be a perfectly wetting substrate with theta equals 1. And that completely eliminates the thermodynamic barrier for nucleation. On the other hand, if you take the other limit of a perfectly non-wetting substrate, this would be a contact angle of 180 degrees. In that case, this term here on the right goes to 1, and then the work of heterogeneous nucleation would just be equal to the work of homogeneous nucleation. So for a perfectly non-wetting substrate, basically the nucleus doesn't react with it at all, and it's the same thing as if it's not even there. So most of the time, reality falls somewhere between the two, where you've got a contact angle that is somewhere between 0 and 180 degrees. The closer that it is to 0, the greater the decrease that you have in this thermodynamic barrier for nucleation. So for a perfectly wetting substrate, one of the requirements for heterogeneous nucleation is the matching of the lattice spacing of the crystal with of that substrate with the growth habit planes of the crystal that you're trying to grow. This is called oriented overgrowth if you've got good orientation, or more generally epitaxial growth. And in reality, the match is never perfect unless you're seeding it with exactly the same crystal that you are trying to grow. Now, one of the ways that we can develop some of the kinetics of the crystal growth process is by making some simplifying assumptions with how the Gibbs free energy of crystallization is evolving as a function of temperature. The simplest assumption that somebody could make is to assume that the delta H and that the delta S are independent of temperature in, let's say, a narrow temperature range around the melting point. And if that is the case, we write the delta G here is equal to delta H minus T delta S. And taking the temperature derivative of that, if delta H is a constant with respect to temperature, that goes away. And what we're left with is just minus delta S. And then integrating both sides from, let's say, our reference point of the melting temperature Tm to some new temperature T, that would give us the difference of the Gibbs free energy between that new temperature T and the melting temperature Tm. And that would be integrating the right-hand side of this equation. This can be approximated by minus the delta S times simply the temperature difference, be T minus Tm. So if we write that as delta T, so T minus Tm is delta T, and then the entropy difference is delta S sub F, the entropy of fusion, then the overall change of free energy with respect to nucleus formation is just the product of those two factors, the delta T times delta S. And we know at the melting temperature by definition is where the Gibbs free energy of the liquid phase is equal to the Gibbs free energy of the crystal phase. So the delta G sub X must be equal to 0 at the melting temperature by definition. Using that then as the reference point, then we can relate this delta S of fusion back to the heat of fusion, the enthalpy change of fusion. And so this delta S sub F can be written as the delta H sub F over Tm, the melting temperature. So an approximation to this change of Gibbs free energy due to crystallization is delta T times the heat of fusion, delta H sub F, divided by the melting temperature, T sub m. And this assumption would be valid at temperatures that are near the melting temperature, Tm, where we've assumed that there's no temperature dependence to the delta H or the delta S. Now, taking this expression then for the delta G sub X, if we substitute this back into our previous expression from classical nucleation theory, where we have the thermodynamic barrier of a minus W star over KT, and then we use our W star that we just derived from our assumption of a spherical nucleus, and then substitute this in for the delta G sub X, then the overall expression can be written as that the nucleation rate is equal to N, so the number of atoms per unit volume, times our vibrational attempt frequency nu, times our thermodynamic factor for overcoming the thermodynamic barrier. So this is our Boltzmann probability, e to the minus, and then this is written in terms of the melting temperature Tm, the heat of fusion here, delta H sub F, the surface tension here, gamma, and the temperature T. And then we still have this kinetic barrier here. The kinetic barrier is the barrier for crossing, for an atom to cross the interface between the liquid phase and the nucleating crystal. Now, if we were to plot this, we would get a curve that looks like on the right. So if this is the temperature here on the y-axis and the rate of nucleation on the x-axis, if we are further to the right, that is a higher nucleation rate. That means that we would be growing these crystal nuclei at a faster rate. If we are at the melting temperature, the nucleation rate must be equal to 0 because there's no thermodynamic driving force for nucleation to occur. At the melting temperature, the Gibbs free energy of the crystal is equal to the Gibbs free energy of the liquid. So there's no thermodynamic driving force for nucleation to occur until you cool the system below the melting temperature. Now, what we observe is that below the melting temperature, there is a kind of narrow temperature range where the nucleation rate is very small, because at these temperatures that are just a little bit below the melting temperature, the thermodynamic driving force for nucleation is there, but it's still very small. And this is called the metastable zone of undercooling. You've got a very slow nucleation rate because the thermodynamic driving force for nucleation is not very big. But the further that you lower the temperature, the greater the driving force for nucleation, because as you go lower and lower in temperature, the advantage that you get in Gibbs free energy of the crystal becomes so much greater compared to that of the liquid phase itself. So the further that we cool below Tm, the greater the thermodynamic driving force for nucleation, and that leads the nucleation rate to increase. But then it goes through a peak and then turns around and the nucleation rate decreases. And what's happening there is the contribution from the kinetic factor. So the nucleation rate initially increases as we lower the temperature because it's got a greater thermodynamic driving force. But as you go to lower and lower temperatures, the kinetics become exponentially slower. And then in the limit of low temperature, the nucleation rate goes to zero because the kinetics are too slow to observe. And if you take the limit of absolute zero temperature, the nucleation rate must be equal to zero because nothing is happening in the limit of absolute zero. So we've got two different regions here in this higher temperature region. What we're limited by is the thermodynamic part. And below this peak in the lower temperature region, the limiting factor is the kinetics. And where we have this maximum here, this maximum and nucleation rate is where we have the ideal balance between thermodynamics and kinetics. This is where we've got a sufficiently large thermodynamic driving force for nucleation to occur, and the temperature is still high enough to allow for fast kinetics. So the maximum of nucleation rate occurs at the temperature that achieves that balance between the thermodynamic and kinetic effects. So that's step one, nucleation. Step two, once we form a nucleus, the next step is to grow the crystal by adding more atoms to that nucleus. So once we have grown a critical sized nucleus, crystal growth may occur by advancement of deposited atomic layers. So by systematically taking more atoms from the liquid and then adding them to the crystal. And this crystal growth rate depends on how rapidly the atoms can diffuse from the liquid regions to that interface and get incorporated into the crystal. And the kinetics of crystal growth was originally developed by Turnbull and Cohen, and it is a relatively simple model that is based on a double well potential, where if we've got the free energy here on the y-axis, then the atomic position here on the x-axis. Let's consider that you've got a crystal position here labeled X, and there's a liquid position for the atom labeled L, and the distance between the liquid and the crystal here, so the barrier that it has to cross, or this atomic bonding distance here, is A. The distance between the sites here is A. Now, if we are at temperatures that are below the melting temperature, then we know that the free energy of the crystal is lower compared to the free energy of the liquid. And so there is a thermodynamic advantage for atoms to jump from this liquid location over this activation barrier and then get incorporated into the crystal. So this free energy of crystallization here is labeled as delta G sub X, and the minus sign is because there is a negative free energy change in going from the liquid to the crystal itself. So that's why it's labeled as a minus delta G sub X. The activation barrier is labeled as the activation barrier of going from this liquid state over this transition barrier, and that here is labeled as delta E prime. So the frequency of successful jumps from the liquid to the crystal just uses our general formulation from chapter 7. This is the rate of successful jumps from the liquid L to the crystal X. So gamma Lx is equal to our attempt frequency nu times our Boltzmann factor e to the minus delta E prime over kT. This is the barrier of going from the liquid to the crystal. So every vibration is like an attempt to overcome the barrier, and the probability of a given attempt to being successful is just our Boltzmann probability factor, e to the minus barrier over kT. So multiplying those together gives us the frequency of successful jumps from the liquid to the crystal. Now, we may also have atoms that leave the crystal and go to the liquid, and in that case, the frequency of successful jumps from the crystal to the liquid is gamma XL from the crystal to the liquid. That is equal to the attempt frequency nu times the Boltzmann probability factor accounting for that barrier. And that is a larger barrier because if we go from the crystal to the liquid, that barrier is the summation of the delta E prime and this minus delta G sub X. So that barrier goes from this deeper minimum. So the effective activation barrier is larger. It's the summation of these two terms. So we've got delta E prime minus delta G sub X over KT. So the net crystal growth rate is then the difference between these two rates. The net crystal growth rate here, U, would be how many atoms are we taking from the liquid and adding to the crystal, minus the rate of the reverse transition, leaving the crystal and going to the liquid. That difference between these two rates is this gamma Lx minus gamma XL. And if we multiply this by the distance that they have to travel here, this gives us the net crystal growth rate in terms of a linear distance per unit time. And now taking our expressions for these two different gamma factors here and combining the common factor of e to the minus delta E prime over KT, the overall crystal growth rate U is this atomic jump distance, A, times our vibrational frequency, nu, times the exponential of minus delta E prime over KT, and then times this factor 1 minus E to the delta G sub X over KT. So there's two different terms here, one which is our activation energy term, and then the other term which accounts for the free energy difference between the crystal and the liquid. So if we are at temperatures that are above the melting temperature, at temperatures above the melting temperature, the liquid is in equilibrium, which means that the delta G sub X is positive. That means that the system is thermodynamically favored to stay as a liquid instead of a crystal. If that's the case, the crystal growth rate is negative. In other words, the rate of atoms leaving the crystal and going into the liquid is greater than the rate of atoms coming from the liquid and being added to the crystal, which means that the crystal is going to dissolve or melt at any temperature that is above Tm. So the crystal growth rate will be negative. The crystal will shrink over time. If we were at the temperature T equals Tm, at the melting temperature, the delta G sub X is 0, and that would lead to a 0 crystal growth rate. And if you are at very low temperatures approaching absolute 0, the crystal growth rate would also be 0 because the kinetics of the process are 0. Now, there is a modification to this theory that was developed by Turnbull and Cohen that was subsequently taken further by Wilson-Frankel. Wilson-Frankel theory then relates the kinetics of this process to another kinetic property, which would be the diffusivity D. And the assumption with Wilson-Frankel theory is that the atomic mechanism that governs the crystal growth rate is the same as the atomic mechanism governing diffusivity. And if we do that, if we make that assumption, the diffusion coefficient D can be expressed as the square of the distance that is jumped, so a squared times the frequency, nu. This will give us the correct dimensionality for the diffusivity in terms of a length squared per unit time, multiplied by e to the minus, and then if it's the same activation barrier between diffusivity and crystal growth, then the activation barrier here would be delta E prime over KT. And if we take this definition of the diffusion coefficient and we substitute in for this, this Boltzmann term here, then we can write the crystal growth rate as a function of the diffusion coefficient D. So in other words, this is an alternative formulation of the crystal growth rate written in terms of the diffusion coefficient D, where with this equation, the crystal growth rate becomes the diffusion coefficient D over A times then 1 minus exponential of delta G sub X over KT. Now this can be taken even further if we combine the Wilson-Frankel theory with the Stokes-Einstein relation. Remember that the Stokes-Einstein relation relates the diffusion coefficient D to the inverse of the shear viscosity of the liquid eta. So if we make the further assumption that the Stokes-Einstein relation is valid, we can rewrite this diffusion coefficient in terms of the shear viscosity of the liquid and have another formulation of the crystal growth rate, which is now a function of the shear viscosity eta. So there's kind of three different ways that we can write this. One is in terms of an activation barrier. The second is in terms of a diffusion coefficient, which assumes that the activation barrier is the same as for diffusivity. And then the third way to write it is assuming the validity of the Stokes-Einstein relation. This can be rewritten in terms of the shear viscosity eta. And this is an example that actually shows quite good agreement with this description of the crystal growth rate in terms of the viscosity. This is for the crystal growth rate of cristobalite from liquid silica. This shows the rate of crystal growth as a function of temperature. The melting temperature is where the crystal growth rate is 0. If we are at temperatures that are above the melting temperature, this is where we have a negative crystal growth rate because the crystal is melting at temperatures higher than Tm. If we are at temperatures that are below the melting temperature, the crystal growth rate increases because the thermodynamic driving force for crystal growth is increasing. These points here are the measured data points of the crystal growth rate. The solid curve here is what is calculated based on this equation shown on the left. Now, as before, there is a maximum of the crystal growth rate. This maximum occurs where there is the ideal balance between having a sufficiently large thermodynamic driving force for crystal growth, while at the same time having fast enough kinetics. If you go to temperatures lower than where this maximum occurs, then we come in this kinetically dominated regime where lower temperatures mean that we have exponentially slower kinetics. And then this is going to decay down to a 0 rate in the limit of very low temperatures. So again, there's kind of a specific temperature where there's an ideal trade-off between thermodynamic and kinetic effects. So if we combine the nucleation and the crystal growth rates, what you see is something as shown here. So this is the temperature on the y-axis, the rates of nucleation and crystal growth on the x-axis here. What we had initially from nucleation was that the nucleation rate became 0 here at the melting temperature. That was increasing as we increased the thermodynamic driving force, and it goes through a maximum and then turns around and in the kinetically controlled region becomes smaller as the kinetics become so much slower. Likewise, for crystal growth, there is a maximum here that is the ideal trade-off between thermodynamics and kinetics for that particular process. A couple of differences are that the balance between thermodynamic and kinetic effects is somewhat different between crystal growth and nucleation processes, and therefore there is a difference between the location of these peaks, where the peak for crystal growth tends to occur at higher temperatures compared to the peak for nucleation. Another difference is that if you take this rate of crystal growth, which also passes through 0 at the melting temperature, if this goes to even higher temperatures, the rate of crystal growth becomes negative at higher temperatures because the crystal is melting, whereas the rate of nucleation just stays at 0. Now, if we want to have crystal formation, we need two things to happen. First, nucleation has to happen, and then crystal growth has to happen. So if we are at a temperature that is in this shaded region here, in this shaded region, this is where we have both nucleation and crystal growth happening. So if we are, say, here, you can have nucleation happening, and then crystal growth will happen after a critically sized nucleus forms. So you could hold the system here at this constant temperature, have both the nucleation process happen and the crystal growth process happening at the same temperature. So if you've got a large overlap here between the nucleation and crystal growth curves, that means it's very easy to crystallize if you hold the system at one of those overlapping temperatures. The problem is that you don't have independent control over the nucleation and crystal growth processes if you are in this overlap regime, because both processes are happening at the same time. If you want to control these processes independently, then you want to be in a region first where you can nucleate and control the population of nuclei that you grow, and then heat the system up to the region where the crystals can grow from those nuclei. So you'd want to have separate steps for both nucleation and for crystal growth in order to independently control the volume fraction of like the number of crystals that you grow and then the size of those crystals. The number of crystals per unit volume is controlled by nucleation, and then the size of those crystals is controlled by crystal growth. And so in that case, where you want independent control, you actually want a greater separation here. So you want a greater non-overlapping region between the nucleation and crystal growth curves. So you can do first nucleation on its own, followed by crystal growth on its own. But let's start off with just a kind of an isothermal hold here, so a constant temperature hold where the nucleation and the crystal growth are happening simultaneously. If that's happening simultaneously, the equation that describes the rate of crystallization is called the Johnson-Mehl-Avrami equation. And this combines the nucleation equation with the crystal growth equation, where the nucleation happens first, followed by the crystal growth after it hits critical nucleus size. And the Johnson-Mehl-Avrami equation gives us then the volume fraction of crystals X in the system, which is defined as the volume of the crystals Vx divided by the total volume of the system. So X is the volume fraction of crystals. And this is equal to 1 minus exponential of minus pi times the nucleation rate I, the cube of the crystal growth rate U, time to the fourth power over E. And if we are in the limit of a small fraction of crystals, so in other words, if this is a small rate, then we can do a Taylor series expansion of this exponential, just keep the first term and simplify this as 1/3 pi I U cubed t to the fourth power. This would be valid in the limit of a small volume fraction of crystals. And with this Johnson-Mehl-Avrami equation, this gives us the overall crystal growth rate, or the rate of crystallization as a function of both the nucleation rate and the crystal growth rate. And we can solve that equation at different temperatures. So for different isothermal holds at different temperatures to get what population of crystals that we would expect for different times. And if we map out a contour of a constant volume fraction of crystallization, so a constant X, then that can give us what's called a time temperature transformation diagram, as shown here, where we've got temperature on the y-axis, time on the x-axis, and then a contour here that would be a contour for a given value of x. So like x equals 10 to the minus 6. This would be 1 part per million crystal, which is a typical detection limit for XRD, for being able to measure whether a crystal is present. And what this time temperature transformation diagram tells us is that if you want to get exactly a certain level of crystallization, that you want to, say, cool from the melting temperature Tm, where no crystallization occurs, and have this cooling path that just exactly touches the contour of that particular level of crystallization. So if this contour is, for example, 10 to the minus 6, if you had this cooling path going from Tm down to room temperature that exactly touches that, that would give you the desired volume fraction of crystallization. And then the slope of this curve gives you the cooling rate that you need to achieve that level of crystallization. So these time temperature transformation diagrams are useful to tell you, how fast you need to cool something to keep crystallization at a particular level. If you take this contour and you lower the amount of crystals, that would be moving the contour to the left, which requires a faster cooling rate, so you don't have as much time to crystallize. On the other hand, if you wanted a greater fraction of crystals, you'd be moving this contour to the right, which means that you need to have a lower slope here, or a slower cooling rate, in order to allow for more crystallization to occur. Now, one of the applications of nucleation and crystallization was invented by Dr. Don Stuckey from Corning Glassworks. And he was the inventor of glass ceramics, and he discovered this initially by accident. He had some molten glass that he put in a furnace. He thought that he had set the temperature at one value, and when he came back the next day, he discovered that it was actually like 300 degrees hotter. It was like 900 degrees C instead of 600 degrees C. So that was his first mistake. And then when he opened the furnace, he saw that it wasn't a transparent glass, it was white. He took it out, set it on the table, and he accidentally bumped it and it fell onto the floor, fell onto the concrete floor. And much to his surprise, instead of shattering, it actually bounced. And so he had inadvertently made a material that had a really high fracture toughness. And he did this by being the great scientist that he was. He went back to study the microstructure to figure out what he had done and learn how to control it. But he had done this by having separate steps of nucleation and crystal growth, where he could take the liquid here, the liquid that is formed into whatever shape that you need to make. So this is liquid state forming, holding it at some temperature where the nucleation rate is high, but the crystal growth rate is low. And the longer that you hold the system at the nucleation temperature, the greater the number of crystals that you will get per unit volume. So this is controlling how many crystals you have. Then if you take this and heat it up to the temperature where the crystal growth rate is a maximum, that is controlling, or how much time you spend at that growth temperature tells you how big the crystals are getting. And so you've got independent control here over the number of crystals that form and how big they are. And by controlling how much time is spent at the nucleation versus crystal growth temperatures, you can get a pretty precise control over the microstructure. And then once you're done, you would cool this down to room temperature, and that would freeze in that particular microstructure. And this led to a whole new family of very successful products for Corning. Dr. Stuckey actually won the National Medal of Technology. You can see it being presented to him by President Reagan. And so what we have are microstructures that look like this. This is a floor mica glass ceramic, which has this kind of house of cards crystal structure within the glassy matrix. This is a surface nucleated lucite in a lucite apatite glass ceramic shown in the middle, and a mica glass ceramic shown on the right. And there's been all kinds of products made from glass ceramics, including cooktops, cookware, pieces for space shuttles. It's been very successful. And in fact, if you go to the Corning Museum of Glass, CMOG, you can see some of this Corningware that Dr. Stuckey had invented, which is a glass ceramic cookware. And what you can see is a function of the crystal growth time, where this is a low amount of crystal growth. This gives you the transparent cookware that has smaller crystals. This is like the Corning Visions cookware. And as you increase the amount of crystal growth time, you go up here, and this transparent cookware becomes translucent and eventually becomes opaque. The white one that you show here has larger crystals, and that was commercialized as Corningware. And you can see here as you're continuously changing that, how this continuously changing crystal microstructure is affecting the optical properties. So to summarize, crystallization proceeds by two steps. First, nucleation, and then crystal growth. With classical nucleation theory, we are assuming that the nucleus is spherical, and we are considering two barriers to nucleation, a thermodynamic barrier and a kinetic barrier. Nucleation is considered to be successful if the nucleus grows to at least the size of the critical nucleus, this R star, and that defines also the thermodynamic barrier for nucleation. The thermodynamic barrier can be reduced with heterogeneous nucleation, which introduces a surface or substrate, some sort of interface onto which nucleation can occur. And how much the thermodynamic barrier reduces by depends on the contact angle. We also developed Wilson-Frankel theory for crystal growth rate, and combining The nucleation rate with the crystal growth rate at a constant temperature gives us the Johnson-Mehl-Avrami equation, which can be used to map out time temperature transformation diagrams. And if you have independent control of the nucleation and the crystal growth steps, that's what gives you the greatest control over your final microstructure. An example of that is these glass ceramics invented by Dr. Stuckey. So next time, we're going to go beyond classical nucleation theory. We're going to question some of the assumptions that we made here in this lecture and propose a few different alternatives for advanced nucleation theories that can account for some more complicated forms of nucleation. So I will see you next time. Thank you very much.